by the Perl. And this code is cache and memory efficient. I will again talk a little bit more about it, even though Dhruvo and Philip have also spoken about it in their own ways. And it's NPI parallelized, and it is maintained by a group of owners, which is a smaller group. Then we have a larger group of developers, around 80 people maybe. And the number of users is now exceeding 200. So basically, number of users are those who have downloading, anybody can download. So anybody can download and use the code. Most of the users out of this lot can also check in their changes into the code. So owners basically have this, have the right to give a user permission to check in, right? So we are fairly open community, and it's a live repository on GitHub, and I explained what is a live repository. And there are, so since this code is so variable, there are so many people checking in their changes. So there has to be some kind of a validation, and that is done by means of what are known as auto tests. So these auto tests are run at different frequencies. So there are hourly auto tests, there are daily auto tests, and there are weekly ones, depending on the complexity of the auto tests. And these auto tests, the job of these auto tests is to make sure that the sanity of the code is preserved. So when I was a new user, so the manual gave these following instructions that if I make any change to the code, before checking in, I have to run the level 0 and the level 1 auto tests definitely to make sure that I have not broken anything that is important in the code. And optionally, I could also do the level 2 auto tests. So all these auto tests, it is possible to run them on a normal laptop or desktop. You don't need a supercomputer or a cluster to run these auto tests. You can stick to your normal laptop. So these are not very high resolution or requiring a lot of memory or CPU or even space. So require very little space, but they tell you if the code is preserving its sanity or not. So now, as you saw yesterday in Jon's talk, so he was using really, intense resolution in his simulations, and he's using up to 16,000 processors, for example. Maybe people like Petri and even Axel, they would have experimented with, or Philip would have experimented with higher processors, but it looks like it is more or less working well or parallelizing well, even with such huge number of processors. So this is, I took this figure from the manual where it shows these different lines are this scaling with a number of processor of a particular sample. And all these different lines corresponds to different clusters on which the scaling has been done. And it looks like the time required, the wall clock time required per time step per grid point is linearly decreasing at least till 1,000 processors. So this is an old plot, but I am sure there are newer ones which go beyond 10,000 processors. Yeah, so this is how to obtain the code. Shomridhi will show you how to do it. So basically you need to have JIT installed, and then you can just JIT clone it from JIT. You don't need to have a user ID on JIT. Anybody can just download it. If you have an ID, well enough, you can use that ID, but it is not mandatory. And there is also a recent copy, which is known as the stable version, which is hosted at this as a tarball. So if you don't want to use JIT, you can also download that tarball. And I really strongly recommend that before using the code, you read the manual. And it's a very nice manual, and you will find a lot of things, but not so much in detail, but it will definitely give you an overview. So to use the pencil code, you need the Fortran and the C compiler. And so these are the things, for example, the make commands and the CSH shell or Perl, these are like heavily used. So if you don't have these, there you have to make a lot of adjustments, but all modern computers have these things. And then you also need an MPI implementation for parallelization. And if you want to do visualization, you need Python and IDL and Mathematica also nowadays that Honchi is going to show. Okay, so this is what it means to have a pencil code. So you have already heard this again. So we have in pencil code, we have something known as F arrays, right? So this F array will basically store all your physical variables. So for example, depending on this n var, so n var can go from 1 to 16 or 17 or whatever is the number of physical variables you have. So for example, for a pure hydro code, a compressible hydrodynamic simulation, you will need the density variable and 3 velocity variables. So you need to have space for 4. And if it is an isothermal run, then four slots, so n var equal to 4 will suffix. But if you are not doing an isothermal run, you want to solve the energy equation, then you need 5 variables. So density, entropy, and 3 velocity variables. So n var would be 5 in that case. And this nx, ny, nz basically tells you the dimension of the problem. Now, normally what happens in a code is full chunks. Suppose we want to have full chunks of F array loaded into the cache, which is the memory closest to the CPU. Then there can be what is known as a cache miss. So the idea or the aim of the pencil code, where we pencilize this F array, that's why the name pencil code. The idea of pencilization is to avoid cache misses. Of course, we cannot avoid it fully. So there is something called as cache miss and something called as a cache hit. So depending on, basically, suppose you are cooking. So I'll give a very pedantic example. Suppose you are cooking and you have a particular recipe and you have a spice rack near on your counter, and you can find some group of spices on that rack. Now it's very easy for you to reach out and grab some spice from that rack and use it in your recipe. However, if you don't find something in that rack, now that rack is like your cache L1, L1, L2, L3, I mean, the layers. So the cache basically has these layers of memory, L1 to L3. So if you don't find something in the cache, you have to go over to the RAM. Now the RAM is your pantry. You have to search for that particular ingredient in your pantry, and that will take some time, right? And if you don't have that ingredient at all in the pantry, you have to leave everything and go to the supermarket to fetch that ingredient. Yeah, that supermarket is like your hard disk. So your spice rack is like your cache, your pantry is like your RAM, and the supermarket is like your hard disk. And that is the, and if you have to go to the supermarket, you have to fetch some data from the disk, it is going to take a very long time. That is understandable, right? So but these cache use a very complicated algorithm, a sophisticated algorithm to find out or predict what is the probability that a particular chunk of data will be required by the code. So they have their different algorithms. For example, you may have heard of last in, last out, or for example, last in, first out algorithms. So these are basically some of these algorithms that are used by the computer to decide what to put in the cache. Now, as I said, the cache also has different layers, right? So L1 to L2. So the L1 is a very small chunk of memory. I mean, it is in 32 to 64 kilobytes maybe. Whereas L2 is slow, but L1 is extremely fast. And compare it with L2, which is actually slower than L1, but it can store some more data. For example, 1 MB or 2 MB of data. And then L3 is the next level, right? So even slower than L2, but it can store slightly more amount of data. So how much data you can fit into, how much data you can store in an intelligent way in the cache determines how fast your code will run. And the idea of breaking things in pencils is basically to make sure, or to help this help the computer to decide really efficiently that all the CPU, all the data that the CPU needs is efficiently stored in the cache. And so in the code, we have MPI communication before every time substep. So basically, I mentioned earlier that we use this Range Kutta method, which Naveen has also covered in his lecture. Maybe he will say something about it today as well. So it is a 3-step process. The RK3 is a 3-step process. So there is this calculation that is being done for every 3 sub-steps, and the same calculation is repeated. So the communication is done before every sub-step, before taking the time step. So basically what happens is real boundaries and interior boundaries are exchanged between different processors. And after that, all derivatives, like for example, you want to calculate the curl of, say, the vector potential, or you want to calculate the curl of velocity. So basically these, you will find these commands like curl of F IAA B. So which basically means that you take this index IAA, which corresponds to the vector potential. You take that vector and calculate the curl of it. But this is also again done in form of pencils. So let me again just graphically quickly go through this, because this also has been covered, about this communication and presence of physical and internal host zones. So basically, suppose you want to have a grid where you have 9 grid points. So your problem size is 9 grid points, essentially in the X direction. But you want to divide these 9 grid points into 3 processors, PROC1, PROC2, and PROC3. So the PROC1 is responsible for first 3 grid points, PROC2 for 4, 5, 6, the next 3, and the last one for the last 3. Now, since we are doing this central finite differences of 6th order, we need 3 ghost zones before and 3 ghost zones after this boundary. Right, so we pad the actual domain with ghost zones. Now, when the domain is decomposed into different processors, so this is what the PROC1 gets. So it gets these it gets this points 1, 2, 3, with which it is in charge of evolving with time, and additionally it also has space for 4, 5, 6 ghosts. 4, 5, 6, which are basically these points from PROC2. It does not do anything to the ghost zones from PROC2, but it receives these ghost zones from PROC2. And it also has these internal ghost zones on the left-hand side. So this processor, each processor will now have 9 total points, out of which 6 are ghost zones. This is a waste of doing it this way, but I'm just showing it because I don't have to draw so many grids. I don't have to draw 512. This could have been 512. So I'm just giving a very simple example. So each processor now has these internal points, which it is responsible for to do evolution in time for the time stepping, and ghost zones, which it receives through boundary communication, out of which these red ones for the PROC1 is the internal ghost zones. Similarly for PROC2 is in charge of 4, 5, 6, and it will evolve those, but it will receive the internal ghost zones from PROC1, and it will receive the internal ghost zones from PROC3. So there will be communication needed to exchange these grid points. So PROC2 will ask PROC3 that please give me the values of grid points, values at grid point 7, 8, 9. And PROC3 will communicate that to PROC2. Similarly, PROC3, it has an external ghost zone, 3 external ghost zones and 3 internal ghost zones, just like PROC1. So PROC3 is going to communicate with PROC2 only, asking it for the values at its host zone 4, 5, 6, which are actually internal zones for PROC2. Right? So that is basically the host zone communication. So if at this point, if there are any questions, then you can feel free to ask. Are there any questions? If not, then I will. No questions. Okay. So basically, again, this is the sixth order finite difference. And then we also have upwinding to avoid wiggles. This also Naveen has explained in his lecture. So basically, when you do upwinding, it is like adding a hyperdiffusion term like del square, del 6 to your central differencing scheme. Right? So this is the structure of the code. So basically you have the main code tree. So when you download your pencil code, it will make a pencil code directory on your computer. And if you look into that directory, you will find these subdirectories. The one called SRC stands for source, is most important. And then you have the ideal and the doc for documentation, and there are some bin directories and sample directories. So these bin directories have some useful shell command files, which we also use to compile the code, for example. And there are some other utilities, like, for example, preparing the data directory. So you want to prepare the subdirectories in the data directory. So again, there are some utilities in this bin directory. Now the main source directory has these particular files. So the most important is the make file. So the make file tells you what are the default modules that will be compiled by default. And then there are these start and run.f90, which basically, so the pencil code, you first initialize using start.f90, the start.x, and then you run it using run.x. So these are the basic files, start and run. And when you start, all initialization is done using the start. And when you run it, so you use that initial condition and then evolve it in time. So the run.f90 actually further calls this time step derivative. And one of the most important subroutines, most important modules in the pencil code is EQU module, stands for equation. Now in the equation module, so there are these different calls, further subroutines that can be called inside the EQU module, which is you can either have hydro or no hydro, density or no density. So basically in pencil code, we have this, you either have a module or you don't have a module. So basically you avoid these more complicated pre-processor directives by having what are known as switchable modules. So you either solve the Navier-Stokes equation or you don't solve it. When you don't solve it, that module, the no hydro module, is actually a dummy module, right? So it does not actually do anything. There are empty subroutines. If you just open the no hydro module and check, all you will see is empty subroutines. So they are actually not doing anything. So these are dummy ones. Same with density and entropy. And suppose you go to a particular sample, you will see a lot of these samples. Inside the sample are the runs through which the auto test is running weekly, daily, and things like that. So one of the samples that I frequently use is convective slab. So it's basically a slab which looks like this. I think, yeah, something like this. And you have convection going on in that particular slab. So these are run directories. These are actual run directories. So inside that run directory also you will have an SRC directory. Now this SRC directory, initially when you have just downloaded the code, it only has two files, makefile.local and cparam.local. Now this makefile.local will tell you the modules, the physics modules and the other important modules that are being used by that particular sample. So the settings in the makefile.local overrides the settings here. So this is a default one, which is existing in the actual SRC directory. And makefile.local will override those settings in the SRC directory. Right? But to further run this code, Shomridhi will show you how to link the source files here and things like that. So there is another sample called interlock flux rings, for example. Now in the sample directory, you can also create your own sample, have your own SRC directory, which will contain your own makefile.local and cparam.local. So normally what we do is we take a sample which matches nearest to the run that I want to set up, and I copy those makefile .local files from that SRC directory to my SRC directory, and then I will modify them. So the makefile.local will basically have these kind of switches. So you want to use a particular physics module, you want to turn off a physics module or turn on a physics module. And cparam.local is basically going to set the number of CPUs you are going to use, the number of CPUs in each direction, X, Y, and Z. And also it will set the number of grid points. And Dhruvo was showing yesterday that if you have particles, then you will also have some information about the number of particles. Now these things have to be given to the compiler before you make the executable. So whenever you make changes to makefile.local and cparam.local, always remember to compile the code. Otherwise, your settings are not going to be included in the executable file. So yeah, so here I again give an example of how to set this cparam.local. So suppose you have n CPUs and you distribute it likewise. Okay, so you have these grid points first. So 64 grids in X, 128 each in Y and Z direction. You have to make sure that nx grid is divisible by nproc x. Suppose you had nproc x3, then you won't be able to distribute your grid points properly in the number of processors in the X direction, right? So you have to make sure that nx grid by nproc x grid, it gives you an integer number. Same for ny grid by nproc x and nz grid by nproc z. So once you do this, so and the numbers that you can calculate from here, so 64 by 128 by 128 becomes 32 by 16 by 16. So this is the part of the domain which each processor is receiving, right? So, and the number of CPUs is basically the product of nproc x, nproc y, and nproc z. So you also have to make sure that you distribute the product of these three quantities, last three quantities, is equal to the number of CPUs. Otherwise, your code will not even compile. Okay, so here is what I was saying, and probably was not clear about the pencil code being modular. So you can either use the magnetic module or the no magnetic module. If you're doing a just hydrodynamic run, then you say magnetic is equal to no magnetic. And hydro, and if you are if you're doing a kinematic dynamo simulation, for example, you can set your hydro in the makefile.local, the hydro hook in the makefile.local to no hydro. And similarly for, these are the examples. And then you have entropy. There's an entropy hook in the makefile.local, which you can set to isothermal or isothermal if you want. You can set it to no entropy if you want to do isothermal runs, for example. And if you want to solve the energy equation, there are a lot of different options available. Then you can either solve for the detailed radiative transfer, or you can switch off radiation. So for most runs, we can switch off the radiation, except for when you are dealing with stellar atmospheres, for example. And then also there is dust velocity or no dust velocity for planetesimal formation samples. And then there are other examples here, for example, chemistry or no chemistry and things like that. Right? So just to go over everything again. So this is pencil code is an alternative to spectral schemes. It's efficiently parallelized. There is no restriction on boundary conditions. In fact, you can have user-defined boundary condition if you so wish. But there are a lot of boundary conditions already available. So before you rush to code your own boundary condition, you are advised to look through the boundary condition module about if that boundary condition already exists in that module or not. And there are different grids possible. So presently there are cylindrical, spherical, and Cartesian grids. It can be equidistant and non-equidistant. But in the spherical grid, the problem is that you cannot go up till the poles because your sine theta is going to go to 0, so that your time step will become very small. So people who do spherical simulations, they do it in a wedge rather than in a full sphere. But that is a limitation of the finite difference schemes. And we use non-conservative schemes mainly. So I think that has a little bit of a historical significance, because when this code was made, it was for dynamo simulations, and conservative schemes don't conserve helicity. So the helicity is a very important quantity when you are doing dynamo simulations. So since there is no such scheme for helicity, so all the other, it does not help. These conservative schemes do not help in the dynamo simulation. So most of the schemes that are implemented are non-conservative schemes. And I have personally found that the pencil code copes quite well with strong stratification as well as temperature contrast, for example, in the solar atmosphere. So now I already mentioned, and other people also did, like Philip, I think, and maybe also Naveen, about F and DF arrays in the pencil code. So the F array basically stores the physical variables, and the DF array stores the right-hand side of the equation you are trying to evolve. So I have just written it down in a very simple way. On the left-hand side, you have d by dt of ln rho velocity, S is entropy, and the magnetic field. And the right-hand side, you have array, the DF array, which is again a function of these variables. And we are, of course, using this Runge-Kutta time stepping scheme that has already been covered by Naveen. So we have this F array, and you can apply this deriv module. This basically consists of these different ways of taking finite difference derivatives. So if you use a 6th order derivative, you can use a 2nd order. Now there is also an 8th and 10th order derivative. So the advantage of the higher order derivatives is that you are reducing the numerical diffusion in your code. So once you apply this deriv modules to the F array, you get what is known as a pencil case. Since all these F arrays can be broken up into mx multi, so for example, you have this I ln rho variable in the F array, and this F array for the density can be broken down into mx multiplied by mz, sorry, actually not mx by my, but it is more like nx by ny pencils. So the pencils don't have the boundaries. So the F array, the full F array stores the boundary, but the pencils are without the boundary. It only has the internal grid points of that particular processor. And all of these pencils are 1D arrays. So basically it can either be 1 by nx, for 1 by nx, where nx is the number of grid points in the n direction on that local processor, or it could be 3 by nx in case it is for example the velocity pencil. The velocity pencil is stored as 3 components, so ux, uy, and uz. So you have these 1, 2, 3, so the vector pencil, and there are scalar pencils. So you have this pencil case which is computed from the F array. And then all this, you can do a lot of mathematical operations on this pencil case to arrive at terms which are in the DF array. And then this DF array is used in the time step.f90 to advance your code. So is there any questions so far? Can you see any raised hands? Okay. Yeah, so if there are no questions, once again, I am showing this distribution of processors on distribution of grid points on processors. So basically you have these things known as L1 and L2, right? And so for the entire domain, your L1, for example, in this example, L1 is 4. So you have to count your grids from the ghost zone. So 1, 2, 3, 4, and then 5, 6, blah, 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 till 15. So you're going from 1 to MX, which is 15. Now, after you have divided it into different processors, your local, so there's a local value of L1 and L2, which is in this case 3 and 6. And plus you have the ghost zone. So you're basically storing the array size, which is 1 to MX in proc 1, but your pencil size is only 1, 2, 3, is 3 from L1 to L2. So the pencils do not have the boundaries included. And then Dhruvo mentioned the most important MN loop, where basically the DF array is being calculated, right? So basically what you do is you pencilize inside the F array. So for example, you can define pencils inside the pencil array. You can do operations on those pencils. You can calculate divergence, curl, grad row, u dot grad row, and terms like that, and then store them as pencils. And the end of it, you will get an updated DF array. So we normally do not modify the DF array outside this MN loop. This MN loop exists in a module known as EQU. So that I think you will be shown later on as well. So you have already seen these equations, the fluid equations and the hydro equation, which was shown by Shohel. So here in the Navier-Stokes equation, for example, you have these velocity terms. So all these terms have velocity, except for this first term, which is the pressure term, and then the gravity term. So the hydro module does not calculate the pressure term in the hydro module. What it does is asks for this particular term from the entropy module where it is calculated. In case you are isothermal, then this calculation is done in the no entropy module. And for this term, the gravity term, the hydro is going to ask the gravity module. So we normally use gravity underscore simple, for example, for Cartesian gravity. So these two terms is computed outside hydro and then given to the hydro module. So similarly, and then to calculate this term, you have to use what is known as an equation of state. So there are several equation of states available in the pencil code. The simplest one being the ideal gas equation of state. And then one of the equation of state that I use as well as my students use in their work is this equation of state, where you have 5 different species. And then essentially it is an ideal gas equation also, but where this mu is actually a function of the ionization fraction. So there are these different ways of calculating these quantities. And if you want to read in detail about stellar atmosphere, I would invite you to read this this paper in the special issue of the pencil code, which was published in GFD. So there we have basically outlined this method of calculating this equation of state. And then you also have MHD, where there are 2 different ways of calculating the magnetic field. So the pencil code has all these 2 different ways. One is called magnetic, which is basically solving for this vector potential. The curl of A gives you B. And there is another module known as B field, but I personally don't use it because it might involve cleaning the divergence. So a lot of other codes, they do this divergence cleaning, and they also use sophisticated algorithms for that, which can actually get messy. One of the problems, if you use this vector potential that is solved, is you don't have the problem of the gauges, but again, you don't have the problem of these divergences, but again, you have to set your gauge and make sure that all your input and output is analyzed in the same gauge. So the simplest gauge that exists in the pencil code is the while gauge, where basically you set this sign to 0. You also have resistive gauge, and now I think there's also the Coulomb gauge. Okay, so now there are several numerical challenges. For example, for people like me who do stellar interiors, to tackle these large Alvin speed constraints. So recently we also coded a particular correction in the magnetic module known as the Boris correction. So this is basically a semi-relativistic correction to the Lorentz force by modifying the by including the displacement current in the Maxwell's equation. So when you do non-relativistic simulations, the hydromagnetics is non-relativistic. It basically means that you are neglecting the displacement current. So to take care of that, there is also a correction here. So basically what happens is, this is the actual equation where current is curl of B and the displacement current. And the electric field is just U cross B. So you can write down your Lorentz force and including this displacement current, and you will have some correction terms. So what this basically means that when you calculate the Lorentz force for the hydrodynamic equation, which was basically this term here. So this term here is not the correct Lorentz force anymore when you are working in a working at high Alvin, working in a regime with high Alvin speed. So you have to correct it. So basically that involves increased inertia in the direction perpendicular to the magnetic field. So in the direction of the magnetic field, everything is still hydrodynamic. Whereas perpendicular to the magnetic field, you have an increased inertia, which basically means the fluid has difficulty moving perpendicular to the magnetic field because of these terms here. And then you essentially have a reduction in the Lorentz force. So basically you are kind of limiting the Lorentz force there. So this kind of a correction helps us work with stellar interiors at a much lower viscosity than a lot of other codes. So you can go to lower viscosities and still have a code which does not crash. Now I go to the equation of heat, energy, or entropy. So in the pencil code, you have the entropy module, which basically is solving this equation for ds by dt. And you have all sorts of these terms in the right-hand side. So the heating, cooling, the thermal conduction, ohmic heating, and the viscous heating terms, right? So this equation is normally used for convectively unstable simulations. For example, you want to do a simulation where the convection will be, the convective instability will be excited. For example, in a stellar interior. So there, you know that for convection, to satisfy the Schwarzschild inequality, you need to have ds by dr less than 0. Right? So it is natural to use this entropy variable for your setup. So you can immediately tell by plotting, plotting the spatial dependence if your setup is convectively unstable or not. But for simulations like stellar atmospheres, we would prefer to have temperature, because the input, for example, we give input from a solar module, right? To the so it has a photosphere, chromosphere, transition region, and corona. So there is a particular stratification, for example, Val 3C or FAL or anything like that. That kind of stratification, you can read it from a stratification file where they'll give you the temperature, actually the log of the temperature. So the reason we use the log of the temperature is same as why we use the log density. Basically, we want to avoid negative temperatures. So there it is okay to use the log T expression where you don't care for convection, right? So these are, for example, this is a equation in all its glory that can be used for stellar atmosphere. So you have this left-hand side, where you have the convective derivative of the temperature. And then you have these conduction, heat flux, radiative heat flux, and then you have the ohmic heating, viscous heating, shock viscosity, and this last term is something related to optically thin radiative cooling, which does not involve invoking the radiation module. So this entropy module, which is now solving for, this module is known as temperature ionization. I'll show you in a moment, which is calling this radiation module because it needs to calculate the radiative flux. And in the radiative module, we are basically solving for this detailed radiation transport, where this is the opacity, and you can have your own recipe for opacity. So we use local thermodynamic equilibrium, Shah ionization, and this K is just Rosalind mean opacity in a gray atmosphere, but you can code your new sophisticated way. For example, like in other codes like Neuram and Bifrost, they have non-gray opacities, and they also solve for different species. We have some amounts of such codes here in the pencil code, but I don't think anybody is using this whole non-LTE, non-gray transfer, as far as I know. And for thermal conduction, so you know, for example, in solar corona, you have this Spitzer conductivity. So we use what is known as a heat flux module. So to it's basically go around to avoid the small time steps which comes into play because the conduction velocities or the conduction term is really very large. So that is like a diffusion term. So the time step is very small. So it goes like dx squared divided by the conductivity. So if the conductivity is very large, then your time step will be small. So to go around it, we use a telegraphic equation for this flux, which is also there in the special issue I quoted, and also in a paper by Jorn, Warnecke, and Philip, also in the same special issue where they talk more about this heat flux module. So this is a typical pencil code sample. So basically these are the equations, and then in a particular domain. So this convective slab sample. And then I have just taken it from the manual. So you can plot, if you run that code and you plot, these will be the density, vertical velocity, entropy, and temperature that you see. So it starts with what is known as a piecewise polytropic atmosphere. So maybe somebody will show it in a tutorial. And in any of the samples, there is a file, output file known as timeseries.dat. So this file, you will see a lot of these quantities in this file, which is actually determined by a file called print.in in your run directory. So the print.in will have these things written, IT, T, DT, URMS, UMax. So these are basically some of the from the diagnostic variables, but these have a single value, the scalar diagnostic variables. Either they have been volume integrated, or they are a maximum, minimum of a particular quantity, or they give you the time step constraint because of different modules. So DTC is the time step constraint because of your sound speed, for example. It is coming from the density module. DTU is the time step constraint from your hydro module. It is coming from the Courant condition, where you take, it is dx by u, where u is your typical flow velocity. And for example, here DT nu is also coming from the time step constraint from the viscosity module. So sorry, not the viscosity module. Yeah, it is from the viscosity module. And similarly, DT chi is coming from the conductivity equation, in conductivity term of the entropy module. So you have these different terms, and these are all explained in the manual. So if you want to understand what are the parameters, you can print in to this timeseries.dat file, which is the simplest file that you can plot and see is this timeseries.dat. And what are the variables that you can print in that is given in the manual. So you can read all about it there. Okay, and then I was also talking about this isothermal and adiabatic run. So suppose this is your makefile.local, and you have these tags here, these hooks here. So for a stellar atmosphere, I would prefer to use set my entropy to temperature ionization, where I was solving that complicated temperature equation I showed before. So basically, this equation was being solved in this module here. Now, if you don't want such complicated things in the energy equation, you may have other complicated things in other modules. For example, this was the module Dhruvo was showing yesterday. And in his case, the entropy is set to no entropy, which means it is isothermal. So in the entire domain, the temperature is essentially fixed. So this is the default. So this is the default in the original make file. Now, unless you override it, your run will always be isothermal. Now, a little bit about the special modules. You basically have this. So in the SRC directory, you have a special directory, right? In that special directory, you can choose a special module either to set interesting boundary condition like a boundary forcing, or you want to solve for an equation which is not described by any of these density, velocity, and magnetic field equations, or the energy equation. For example, Jennifer uses a special module called chiral NHT. And Philip and me and Philip uses a module called corona.f90. I use one called solar corona, which is also used by other people. So for different users, we have these different special modules. And you can write your own special modules. So the recipe is, there would be let me go over to the my this thing here. So basically, you will have, suppose you go to pencil code and you see your SRC directory, there will be a file called no special. Now, if you look at this no special thing, it has all the hooks. So this is what I'm showing you: register, special, initialize, finalize, and things like that. So some of these, for example, special calc pencils. So special calc hydro. So it's not doing anything. It's an empty module. Right? It's a dummy module here. Right? But in some other special module, it may be calculating some special terms. So I can, for example, show you what is happening in the special module I use. So for example, you again go to the special calculate hydro. It is doing something here. There is a solar wind, or it is doing something. Even in the density module, there are some hooks here. So here it is doing some great calculation. So this is what you can. So in my case, I am only using it to put some boundary conditions or some unique kind of a forcing. But you may also want to solve a particular equation. For example, d special by dt. For example, some chemical potential or the chiral potential, for example, right? So there are a lot of these special modules which are already available. Axel is using some of these, like gravitational waves, for example. And we are using solar corona as well as something known as twisting jet. So you may want to look at these special modules to find out if what you require is already existing in the pencil code or not. And I'll leave you with some of the references for people who want to start from the scratch. So these are the floating point material that this one Philip was also showing, and it's a very popular one which is actually referenced by all courses in numerical methods. So you may want to go over this. It's a very well written article. And you can also look at numerical recipes, and also this art of it's not scientific programming, art of computer programming by Donald Knuth. It comes in 3 different series. And then you will understand that when you code, what is the best way of, for example, calculating an exponential or multiplying two vectors, or, how should you exactly do it so that your code is more efficient, right? Because your code is ultimately going to be converted to assembly language, and the less amount of, less amount of complexity you can, your code can be complex, but it can be coded in such a way that at the assembly level, it is more efficient than, other methods. So I would, now I think Shomridhi will stop sharing. And while Shomridhi is sharing his screen, I can take questions here or on Slack or whatever it is.
Thank you, Piyali, for this very nice introduction to the pencil code and the related modules. And I'm sure it will be very much helpful to the new users. So if you have any questions, kindly raise your hand.
You can share your screen. Put this now.
I don't think they have questions. Right?
Yeah.
Okay.